Howdy, everybody. Hope you're doing well whenever you are. We're here for a Z3 with Rust course, a little bit of a tutorial. Um, we in the videos before we've used Z3 a little bit, and there was some interest in doing a full kind of course on it. So that's what we're here for. It's I think it is going to take 5 videos to go over it in as much depth as I want, and to review it enough where I feel like it'll be worthwhile. So that'll be the plan. Is the next 5 videos will be specifically about using Z3 in Rust. I think it still applies to other languages. So if you're using in Python, obviously the code's going to get different. But hopefully you'll be able to see with the examples and the homework enough information for you to figure it out if you're using another language. If you're new to Rust, though, that's fine. I think you can still do this course with just maybe a quick tutorial of Rust, so to get you up and running. But anyway, that's why we're here. That's what we're doing. Let's get started. So all of the code, I'll have links down in the description. But all of the code for my project is here in Z3 Rust. So I will link to that. You're welcome to check it out and look it over and try out all the code. The main README kind of goes through the 5 things that we're going to do. So that's kind of the plan of how it will go. We'll start with kind of a gentle introduction. I have 2 little problems that we'll do, and then I'll give you some homework. And that'll usually be the case for most of the days, is I'll give you a little homework assignment. And then the next day I'll give you the answer, or the next video I'll give you the answer to the homework. But do it at your own pace, right? If you need time in between, if you need to pause and work on it. The only thing is the last video will actually solve 3 real, quote unquote, real world problems that I think will really help you do that. And in that case, you won't really have homework in that sense. I use the term homework loosely, by the way. I understand that it's really just learning and growing. But the idea will be is I'll describe the problem, you can pause, work on it, and then you can look and compare my solutions. And, I'm not perfect at Z3 or anything like that. So if there's anything wrong with it, or if you find a better way to do it, or a more interesting approach, I'd love to see it. So feel free to show me that. But the goal is we're going to do an intro. We're going to talk specifically about the solver, then the optimizer, and then do incremental solving, which is where I think there's some really cool powers to Z3. Maybe not for puzzle solving, which is what most of this channel is, but in that sense, I think it's useful. Or sorry, in a business sense, or a day-to-day sense, I think it's really cool. So we'll talk about that, and then we'll have our 3 showcases at the end of it. So that's kind of the plan. So if you're getting started, feel free to check out this repo and try some of the code. Should be able to run it. And of course, if you're stuck on your homework or need help, I think I put some hints in there, but also there's just straight up solutions to it. So if you need some kind of solution to help you get to the point where you feel comfortable, that's fine as well. I think that's it for the getting started. So let's just dig right into it. If you're here and you're like, oh, Z3, I heard of Z3, you may be asking yourself, well, what is Z3? Well, the name kind of is in the repo here. It is a theorem prover. And that can sound a little weird, right? You're like, oh, what does that even mean? What is a theorem prover? Specifically, I'm trying to find it right. Oh, you know what? I think it's in the Z3 guide. Programming Z3. Oh, maybe it's not in here. Maybe it's in my actual thing. Let's look. So in the README right here, what does it say? What is Z3? It's a high performance SMT solver from Microsoft Research. So this is a lot of work they did. Its bindings are in C++, or the libraries in C++, but it's got bindings in Rust and Python and whatever. A satisfiability modulo theories, or a SAT solver also. These are just like computer science terms for solving generic problems over um, uh, where you can say, I want this but not this, and I want this but not this, and then it will figure out if that's actually possible. And then they've gone further to say, oh well, Joe likes this, and Anna likes this, and Bob dislikes this. Can you find the optimal solution to like maximize happiness or make everyone most happy? There's very computer sciencey and mathematical terms for these things, and so you'll see it say module theories and satisfiability. This is a well-known problem. The Boolean satisfiability problem is known to be like a hard problem to solve, right? And so what they've done is said, hey, we can create this solver that's meant to be very high performance to help you with these problems, and make it generally useful. And so that's the kind of the way to think about it. At like a really high level, the example I'd like to give for this thing is, let's assume you have like a problem like I don't know, x plus y equals 5, and then you have 2x plus y equals 8, right? You may have seen something like this before. They're called it's a system of linear equations. The idea is, if you've taken this math before, you can kind of do some stuff to actually figure out what these is. This is a simple enough problem, you could probably just start kind of guessing, right, and figure it out. But you kind of use some logic where you say like, I can turn this into y equals 5 minus x. Oops. 5 minus x. And then I can plug this in here. So now I get 2x plus 5 minus x equals 8. Now I can just solve this to x equals 3, right? So now I know x equals 3. I can plug it into one of these problems, right? We can say 3 plus y equals 5, and now y equals 2, right? So there, I've now solved it. I know for this system of equations, x equals 3 and y equals 2, right? And so this is a kind of problem that these things are meant to solve, right? It also can solve Boolean style problems where you can say A and not B. I don't know what to use here. That I think like the actual thing is like this. We're saying A and not B, right? And so we know like the way that this would solve is if A was true and B was false, right? That would satisfy this equation. It turns out, and if you think about it, you might be able to get there, or you might not. It sometimes it kind of confuzzles me as well. This type of problem is identical to this type of problem. That is to say, it's not identical. I should, maybe to be more clear, is I should say this type of problem down here can be turned into this type of problem up here. And this is a true SAT problem, right? We're asking ourselves, are there some variables for A and B such that this thing is true? And if notice the way I said that, are there some variables for A and B such that this statement is true? We can actually do that over here. Are there some values for X and Y such that these two statements are true, right? So that's what the Z3 solver does. And that's what SMT and thereby SAT does. Is the goal is, can I solve a problem that again, these are like kind of sample toy problems, but you can get very complex problems, and we'll actually show those in some of the problems. Some problems that are almost impossible to reason about But if you plug in the numbers and tell Z3 to solve it, it will do it for you. Okay, so that's what Z3 is. The goal is, do you have some kind of problem that you need to solve that has a lot of constraints? And can you enumerate those constraints? Can you give them to the computer, or in this case, Z3? And then if you can do that, then Z3 will try and fit them and tell you if it's possible or if it's not. I should be clear, like that's kind of the goal of these things, is that it will either return sat, meaning satisfiable, or unsat. There's technically another one. We'll ignore it for now. There is an, I guess I'll just tell you right now, there is an unknown one, meaning it doesn't know, something else happened. This is usually like an error. So like something happened, you ran out of memory, it couldn't solve it. Some during the processing, something was halted, right? And so there's this like unknown one where it says, I don't know, I had to stop, so I wasn't able to do it. But what we're asking ourselves, can this be satisfied, right? So for example, these both can be satisfied, but if you were to ask, like, is there an A and not A, like, could you solve this one, right? Think about it for a second. You couldn't, because if you set this one to true and this one was so this is now false, true and false is false, you could never get this one to be true, so this one would return unsat, meaning it's unsatisfiable. We can't satisfy that problem. Okay, so with that, let's get our system up and running, and let's look at a couple examples. Yeah, so how do we set up Z3 in Rust? So that's actually what most of this is. Well, the first thing you need to do is add it as a Rust dependency, right? If you're using Rust, or the same if you're using Python or whatever, you need to download that library, or use pip install, right? Or cargo install in our case. So we're going to cargo install our Z3, and I'm using version 0.19.6. If you're using a much older version, your code will look a lot different. So I have previous solutions to problems like puzzles where the code looks a lot different. It's changed a lot. By default, though, most of these things expect you to have the bindings, or the library, the C++ library installed. So what does that look like? If you're on, Ubuntu, it would look like this, where you install libs Z3 dev. Like for Arch, I think I installed Z3. Same thing for Mac OS, you just brew install Z3. Windows is, I actually didn't look. They may have like a Choco or a Scoop repository for the Z3 bindings, but you can use like VC package or whatever to get Z3, or you can go download the pre-built binaries. And I should say on that note, sometimes you'll run into an issue where it will take a while to build, especially in Rust. And that's because you may run into an issue where Clippy will try and build the binaries a certain way, and then cargo run or cargo build will try and build the libraries another way, and they're in contention with each other, and you're constantly building and rebuilding. And so you'll sit there for like a minute and wonder why it's continuing to build. And the reason behind that is it's trying to rebuild the underlying Z3 library by hand. Okay. So if you'd prefer not to have to deal with all that stuff, the bindings by hand, I should say, you can enable this GH release feature in your Z3 crate. And what this will do is, instead of trying to build it from scratch, it will go download it from GitHub. So you can do this cargo build features, GitHub release, and then it will, or cargo add with this feature, and it will throw it in there for you. And what it will have the effect of doing is downloading it from GitHub. GitHub does do API rate limiting, right? So if you want to get around that, you can generate your own token. I have instructions on how to do that. So I did try this, and as of the recording, this works. Okay. So that'll get you like set up for Rust and be able get up and running. And again, if you have problems building and it's taking a lot of time, you can try and enable the GitHub release feature, and then it'll download it instead of like pulling it. So you'll actually see me running the actual code from my pre-built stuff, and that's just so I don't have to worry about this. I built it all, but again, these are kind of like the general ways to do it. So with that being said, let's talk about solving a problem, right? So how do we actually go about doing this process? What is like the problem solving process when we see a problem like this? How do we turn that into a Z3 solver thing, right? How do we use Z3 to solve this? And there's kind of like a core concept of like ideas that I want you to get out of this video. Because if these are kind of ingrained in your mind for how you solve a Z3 problem, it's just 3 steps. If you can remember these 3 steps, I think it will get you most of the way there. Any other details you can kind of work out with, looking at the API documentation and stuff. So the first step is define variables, right? You need to define what variables are interesting to your problem, right? So over in this case, it's X and Y, right? We're interested in these variables, X and Y. We have some constants here, 5 and 8 and 2, right? Those are things that we'll plug in. Over here, our constants are A and B, right? We have 2 things right here, right? And they're Boolean ones. I think both my examples are integer ones, but you can use different types, okay? We'll talk about those in another video. So you need to define your variables. So figure out what variables you're interested in, and then make sure you've defined all of those. Then you need to make assertions about those. And so what do I mean by that? These are like the logical constraints. So I probably have said constraints a little bit about here, or before. What I mean by that is these are assertions you're making to the solver. You're telling Z3, here are the constraints you have to work around, right? So in the case of this, each of these are constraints right here. These are our constraints. So our variables are in this case, it's X and Y, and our constraints are X plus X plus Y equals 5 and 2X plus Y equals 8, right? Those are our constraints. And what this is having the effect of doing is telling the solver, hey solver, X plus Y equals 5 and 2X plus Y equals 8. And then the last thing you need to do is once you've defined your variables and you've made your assertions, you then run the solver. You run the solver and you say, hey solver, is there a solution to this problem? So now you say solve. These are the 3 big steps, and this is what I want you to get out of this. This is the general solving problem, right? Now, there are some interesting parts that we'll talk about in future videos, because you can kind of do this iteratively, and so you can have like a hierarchical like loop process where you add variables, make constraints, ask it to solve, and then maybe you mutate some of the variables or remove some or add new ones and add new constraints and then ask it to solve again. It can do all that stuff, right? It can do all of this stuff in a loop. But at the core of everything in the Z3 solver is define your variables, add your constraints, and then tell it to solve the problem. And if you can remember to do those 3 things, you'll be able to figure it out. I would say that these 2 parts can be difficult, though. It seems like two easy steps of defining your variables and what are your constraints. But you can mix those up, right? So I had an Advent to Code problem that I was solving recently, and one of the issues I ran into was I was misinterpreting like what my variables were, I thought like maybe the best way to do it is like the solution kind of looked like this. There was an A, a B, an X, and a Y, right? And I thought that my variables were these, but it turned out my variables were actually these. These were the variables that I was interested in. And so that's just what I mean by this can be hard depending on the problem. So if it takes you some time to get there and figure this out, that's okay. Please don't feel like, oh, this isn't coming together. It can be really hard because in some ways all of these look like they're variable, right? But these were like the, you know, the solution. How do I say this? These were the variables that I was looking to like solve. And like this was actually the constraint. Because what I was trying to do is I was trying to say I want X to be 5 and Y to be 7 or whatever, right? And so I needed to say, hey, give me an A and a B such that, you know, given these values, I can make X 5 and Y 7. That's what I was trying to ask. And so this is all just to say, if it's not making a ton of sense, please understand that it can be hard to figure out what your variables are and what your constraints are. And so allow yourself some time to figure that out with each of the problems, okay? Okay, have we talked enough? Should we get to an actual example? Let's do it. P1. So I'm here in the main source code for P1. And would you look at that? We have a system of integer equations, right? So we're going to try and solve x plus y equals 10 and x minus y equals 2. This is just like this problem right here. We've just got different constraints on it, right? So we're going to follow our steps. First, we create our solver, right? So in Rust, we just say solver new, and now we have this solver that we can assert constraints within it, okay? We define our variables. So in this case, right, we have x plus y equals 10 and x minus y equals 2. Our two variables we're interested in are x and y. And we do that with new const, okay? There is another variable, or another way to do this. It's called fresh const. I don't think I'll use that throughout the rest of the code, but just so you're aware that's there. If you're reusing x throughout your code, using fresh const may help you ensure that you get a new value. And the reason I say that is for the Z3 solver, when you say create a new variable called x, it will assume that variable x applies to the rest of your solver, okay? The rest of the model that it's creating in solver. And so if you ever add another x, you ever think you're adding another x down below here, you won't actually add it. I won't go too much into it, but it's like a syntax tree. So like you may have like it'll actually look more like this. It'll be like I don't know, add 5x 10, right? It'll be kind of like this, right? So if you ever try to add like another variable, like if you ever say x plus 3 equals 5 or whatever, and you want to add this to the thing, it will think these two are the same. And so you just need to make sure as you're like building these that you're not reusing the same variables. And you can use fresh const if you want to help you with that. And you'll get the equivalent of an XO and an X1 in like math parlance, I guess. Sorry, just a second here. Okay. We've defined our variables. Now what is the next step? We assert our constraints. So you can see here, it looks a little funny because I'm borrowing, but otherwise it looks quite like what's up here, right? I say x plus y equals 10, and I give it a literal value 10, right? So I'm saying x plus y equals 10 and x minus y equals 2. So I'm using these variables that I'm defined, but I'm asserting something. I'm applying a constraint. And this is where the solver is saying, okay, now I need to, when I'm solving this problem, I need to make sure that x plus y equals 10 and x minus y equals 2. Okay. So I think this is one of the cool things about like using Rust or Python. I think kind of looks this way as well, is it looks very similar to the actual problem, right? So I think I've said this before. We'll have some examples where you're using like loops and iterators and things like that. And it looks very close to the actual language that you normally write in, the programming language that you normally write in. But under the hood, the Z3 libraries, like the bindings to those libraries, are like pulling, are like using that information to like create those constraints for you. So I think it's pretty cool. Again, but we use this solver.assert to do that, right? So we've created a solver, we've created our variables, and now we're asserting to the solver that these variables have to meet certain criteria, right? They have certain constraints associated with them. So we're saying x plus y equals 10, x minus y equals 2. Okay. And then the last step is we just have to check for satisfiability, right? We tell it to solve the problem. We say, hey, go solve the problem. And the way you do that is we do solver check. Okay. So we've made all these assertions, we've defined our variables, made all these assertions, and now we say, hey, just check. And oh, I do put the unknown in here. Okay, so there's the unknown. So there's three things you get out of this check call. It's either satisfiable, unsatisfiable, or unknown. Again, you'll very rarely get unknown. This has to do with like something broke. This is like the quote unquote error case. These two cases are not considered errors, is maybe the way to think about it. This is saying unsatisfiable is saying I can't solve this problem, right? There's no solution for me to get to this point. And I can show you what that will look like in a second. But otherwise, it will say, oh, this is satisfiable. So there is an actual solution to this problem. And then we can call the model, we can get the model from the solver. So once it's figured out what it is, we can ask it, okay, tell me what it is. Give me the answer. You know, maybe we're just interested in if it can be solved or not, but you almost always probably want the answer, right? So in that case, we say, hey, go give me the model that has the solution, and then we can just print that out, right? So let's actually go look at that now. So if I do target release, part 1 intro. Yeah, there we go. You can see here it is right here, this top section. We'll talk about the second one in a second. Let's just focus on this top part right here. So we know we're solving x plus y equals 10 and x minus y equals 2. And we can say, and then we ask it, is it solvable? And it says, yep, it's solvable, satisfiable. And then we ask it to print out the model, right? And this is what it prints out for us. It says x equals 6 and y equals 4. So for this thing, we know x equals 6 and y equals 4 solves this problem, right? So we could probably, maybe just to show you how it would work, we can derive something that we know won't work or shouldn't work. I actually haven't tried this. We're doing it live, but what does it say now? Again, ignore this part. It says, oh, I can't satisfy this problem. It's unsatisfiable. So it's not unknown. It's not some error. It's literally telling you this cannot be solved. There's no solution to this problem. And why is that? Well, you can think about it for a second, and I don't know, if you're like me, it may take a minute, but obviously you can't construct two values that both equal 10 and 2 when summed together, right? So you could come up with some other problem potentially that would be solvable, but in this case, x plus y could never equal both 10 and 2. I don't know, maybe dimensions have split. The SAT solver is not doing that kind of stuff, right? So we're really just solving a system of linear equations. And if we give it one that is solvable, it will say, yes, I can solve it. If we give it one that's unsolvable, it will say, no, I can't solve it. Okay? So that's what we're looking for. And, you know, when you're solving like puzzles or something like that, obviously you expect to get this. And if you get this, something's broken. But in the real world, maybe if you're doing some like business logic or business processing and you want to say, oh, I have a bunch of these projects and these due dates, can I complete the entire project given this timeline? And you may enter all that information and it will say unsatisfiable. And that doesn't mean that you've done anything wrong necessarily. I mean, you should check to make sure you don't have any bugs. But what it will, but what then that can tell you is, no, I actually can't finish this project given the constraints on the time, right? So that's what, I don't know, you maybe we don't worry about these things anymore, but we used to have like giant Gantt charts that were like how all the stuff gets done, and it would try and solve these type of problems. Well, we can solve those type of problems now with something like Z3, but we can solve generally any problem where, again, we can define some kind of variables and give some kind of constraints. We can tell Z3 to solve that for us, right? And it will tell us, yep, I can solve it, or no, I can't. Okay, let's move on to example 2. You don't always necessarily want to say, hey, is this solvable? Right? In this case, you may actually want to say to yourself, can you minimize or maximize something? Can you optimize my solution to a problem? And that's where the optimizer comes in. And the optimizer kind of sits, like, I think one level higher than the solver. So the solver is just saying, can you do it? The optimizer is also asking, obviously, can you do it? Because it might say, oh, it's not satisfiable. But it's also saying, like, here's the best way to do it. And usually, in most cases, the quote unquote best way will either be to minimize something or to maximize something. Right? So maybe you want to maximize some type of happiness or maximize your profits or something like that. Or maybe you want to minimize something like costs or things like that, right? And that's where the optimizer comes in, and that's where, you know, this is helpful for using. So we follow the same patterns, except at the end we just say, hey, I want you to minimize or maximize something, as opposed to saying, I want you to solve something. So the example we have here is we want to say x is greater than 0, y is greater than 0, and 2y plus x has to be greater than or equal to 10. And then it will say, can you maximize the values of x and y, right? So again, kind of what we're doing here is we want to define our variables, right? Scroll down a little bit. We want to say x has to be greater than 0, y has to be greater than 0, and then what was it? 2x plus y greater than or equal to 10, right? So these are our things. So we need to think about, and we want to minimize x and y, right? So find the minimum values of x and y that meet this constraint. And obviously this one's solvable, but you could give it some kind of like, set of constraints that it would not be able to solve. But let's go ahead and pull out and think what our variables are, right? So we have x as our variable and y as our variable. So our our vars are x and y, right? And then what are our constraints? Well, they're actually right here, right? So we're literally saying x is greater than 0, y is greater than 0, and 2x plus y is greater than or equal to 10. So those are our constraints. And then 3 is the solve, right? We want to solve it. And our solve is we want minimum values for X and Y. And again, this is kind of a toy problem. We're just getting into it, getting started. The homework will be a little bit more, I think, interesting, but it will, I hope you can kind of see already the power of the Z3 solver, right? Is we're only using 2 variables here, but you could easily use 50 or 100 or 1,000. And then we're only using a few constraints for each of these, but you could easily use hundreds of constraints, and it would increase the complexity and make it harder for the solver. But at the end of the day, it's really just the same thing, right? Is you're really just figuring out what your variables are, figuring out what your constraints are, and then asking it to solve the problem. And in this case, the solution is we want to minimize some values, right? And again, you could probably do this in your head, but this is used quite a bit, right? In fact, I think we've used this in Advent to Code before. So if you've seen previous videos where we're solving puzzles, a lot of these are like minimization or maximization problems, right? Like you want to find the closest variable or the smallest number of button presses, or the furthest distance you can go. That's where we're doing this optimization problem, right? As opposed to just, can you solve a problem? Okay. So how does this one look in code though? It's actually not much different, right? Instead of using a solver, we now use an optimizer, but we do the same thing, right? We're going to define our variables, our X and our Y. And again, because this is all in its new function, we don't have to worry about like X and Y overlapping with each other. We have our new optimizer. We're putting those values in there and stuff like that, right? But we say, okay, give me a variable X and give me a variable Y. And then we make our assertions, right? We say X needs to be greater than 0 as well as Y. And then we just make our thing here. Notice I have a couple constants here. You could create variables for those constants, right? Sometimes I think you'll see in code people say like let 0 equals int new const 0 or whatever, like this. No, it won't look like this. It'll be like new from i64 0 yeah, like this. And this is like saying like I have a 0 value that's like a constant value. It's not a variable. These are, even though this says new const, what it means is like new from a constant. So this is a new X value coming from the constant X, right? So this is creating these two are variables. This is an actual constant value 0. And then you'll see people put it in here, right? So you could put it in here and presumably it would work the same way. But because we're in Rust, we can say, hey, give me these literal things. And then same thing right here, right? We just say 2 as an i64 times X plus Y should be greater than or equal to 10, right? These are, again, these functions greater than and greater than are equal. They're translations of like these things right here, right? Oh, there you go. It would actually be really cool if you could, I think it makes more sense to do it this way, but it might be cool if you could actually use the operators. It makes more sense to do it like this because you're almost always wanting to wrap this anyway. You don't want to have those mistakes, right? Of not properly grouping your code. But just to be clear, again, we're just asserting constraints, right? We've defined our variables and then we're creating constraints on those variables. Now, we need to have some kind of objective for this. So where we start to differ is what we want to minimize, right? We want to minimize X plus Y. So we want to find some value where all of these constraints are met, but we want to minimize these two values, right? We want to minimize X and Y. And the easiest way to do that is to just create a variable that's like a sum of those two values, right? So we'll say for the variable Y, our X and Y, for these two variables, we'll create a sum variable. And this has the type, if you look at it, it has a type of int, which is an int in Z3. So not an int from the Rust programming language. It's an int in Z3. And this can then, we can say, I want you to minimize that integer. So just to be clear, this has the effect of creating a new variable called sum, right? Like that's what's we now have a new variable called sum, and sum is equal to x plus y, and we're telling the optimizer to minimize that value. Does that make sense? So in this case, we're saying I just put min right here, but we're actually literally what we're going to do is we're going to have another variable called sum, and we're going to have another constraint here. It's not really, I guess it is, I mean, it fits in this category, but the constraint is sum equals x plus y. And then what we're actually doing here is we're going to call minimize of sum, right? Like that's technically what we're doing here if we're trying to like get into the weeds. But this will be I think as we work on the optimizer, you'll actually see we do that in part 3, that this will become more clear if it's not clear to you right now. Anyway, once we've done that, we can just say, hey, check, is there a solution to this problem? And just like the other one, if it returns satisfiable, we can then go pull out the model, right? And we up here, we just printed the solution right here. You can see we printed the solution. You can actually pull variables out of it though, right? Like if you want to print something, or maybe you want to like turn the model into some JSON object that you're going to send somewhere, you're welcome to like call get model and then pull variables out. I think for future problems, I do it both ways. I do this way as well as this way, just to kind of give you an idea of like, to help remind you that you can do it both ways. But, you know, depending on what you're doing, one way may be better than the other, right? But again, so all we're doing though at this point is printing out the variables that we were looking for, right? How do we find the min of these two values? So I need the model to say, hey, can you give me X? Can you give me Y? And can you give me the sum, the sum of those two values? So remember, these are the variables, and what the way that eval works, like if you look at it in the I don't have my documentation set up for it, but you're saying, hey, give me the variable X, and you'll always just pass true here. Then you unwrap it, turn it into an I64, unwrap it again. If you're not a fan of unwrapping because of unwrap gate, you're more than welcome to like check errors here. Probably the best way to do this one is like use the question mark operator, right? So that's what I would suggest doing, because you'll see yourself doing a lot of unwrapping. That should always succeed unless you have like a logical error in your code, right? Where you probably want it to blow up, I guess. I don't know. Maybe you don't want it to blow up, but you can, you know, use the question mark operator to like bubble up the error into, you know, your function definition. Okay, but again, we haven't done much different than the first problem, right? We've created a solver, in this case an optimizer. We've defined our variables. We've asserted some constraints about them. And then we've created like a minimization variable that says, I want you to minimize this value, okay? And once we've done that, if it returns a value, we can then say, oh, here are the answers. Here you go. How does that look? So let's go try it. Again, well, I guess we've already run this one, but you can see here's the answers, right? So we're trying to create these constraints, and it says, yep, you can solve this. And the minimization values are 4 and 2, right? If you think about this, you could have come up with this solution, right? You can say, oh, I want to put as many values here. I want to put as many values as X because X is worth double. So 4 will get you to 8. But if you do 5 and 1, I guess that still technically works. It puts you over the category. You'd never do 6 and 1 though, right? And you definitely couldn't do 6 and 0, right? Because Y is greater than 0. But this one is one of the best answers, and we'll show you in another video. There may be multiple answers. 4 and 2 and 5 and 1 are like equally viable, right? Those would both work. depending, I guess, based on the variables, you may have more than one like potential possible value. So anyway, that's just something to think about. Here's a system of linear equations again. Here's an optimization. These were the two examples we ran through in our code. So I encourage you to read over this, make sure you understand it, and then let's go back to our README. I have some homework for you. So this is a problem I'd like you to try and solve yourself. Feel free to look through the READMEs again, and I have some links for further reading. I'll also include those in the description on some of this stuff if you're interested in going further. But here's your homework problem. So the homework problem is solve a simple integer constraint problem. So this is similar to the first example. So you just left a bakery with a receipt for exactly $50. You bought 3 types of items: croissants, which were $3 a piece; bagels, oh, I've been learning French, so I try it, croissant, were $3 each. That was terrible, I apologize. I am trying to learn French though, so I recognize my English or my French is not great, but I am trying, I promise. And then bagels were $2 a piece, and muffins were $4 each. So your constraints are: you bought one of you bought at least one of each item. I can read too, people. And you bought more bagels than muffins. The total number of items you bought is 20. So the question is, can you write a Z3 solver to find out exactly how many croissants, bagels, and muffins you bought? So that is to say, here's the price. You spent $50. Here's the price of each of the 3 items. And then here's your constraints. Can you write a Z3 solver to solve this problem? Okay, I think this will be a great introductory problem. I have hints down here. Ignore them if you want to try it yourself. But if you're struggling, there's some hints that will kind of help you out and get you moving. Again, we're learning here. So if you feel like you're not there yet, look at the hints. And if you're really struggling and you just can't figure it out, go look at the solution. I have a solution for each of these in the thing. So that's your homework. So the next video we'll go over that homework and see see how you did. We can compare and contrast my solution to yours. Maybe you did it better than me. That is totally possible. So okay, that's it. I just, in conclusion, would like to remind you, I think if there's one thing I want you to remember, it's like this part right here, right? The best thing for you to remember is, how do we go about solving any of these problems? And it's asking yourself, what are the variables? What are the constraints? And how am I solving it? What am I doing to solve it? Am I just saying, is it possible? Or am I saying, is it, should I minimize something or maximize something? If you can kind of write those things down or have them in your mind, it will make solving the actual problem much easier. So there you go. I look forward to seeing you in the next video for this course. I hope I taught you a little bit of something about Z3. We will get into more meatier details in the next coming videos, right? And I think hopefully that stuff will be helpful to you. We'll talk to you next time. Bye, everybody.